Hi, everybody. My name is Ritisha Padmanabh. I'm a senior product manager here at AWS. In today's session, we'll be talking about how you can monitor, troubleshoot, and get holistic visibility into your AWS networks using VPC monitoring solutions. So, here are the learning objectives for today's session. We'll first learn how you can monitor your network traffic flows using VPC flow logs, how you can get deeper visibility into the actual payload using VPC traffic mirroring. Once you have visibility into your traffic flows, we learn how you can track the network performance of your EC2 instances using EC2 instance level metrics. And finally, we're also very excited to launch a brand new feature that will help you troubleshoot your network connectivity issues, which is the newly launched VPC Reachability Analyzer. Before we get into each of these monitoring solutions, let's just do a quick recap of what your AWS network actually looks like. So you can have multiple VPCs within the various AWS regions that we have. And these VPCs can span multiple availability zones. In each availability zone, you can have both a public or a private subnet, and each of these subnets will then have your EC2 instances. And then you also have a multitude of additional AWS services like S3, DynamoDB that sit outside of your VPC. However, if you were now to double click into that, you realize that there are several other networking components that actually allow you to create scalable and resilient AWS networks. Right, so you'll be connecting to the internet through your internet gateway and NAT gateway. You can connect to your on-premises environments using virtual private gateway or direct connect. You can interconnect your VPCs using VPC peering or transit gateways. And finally, you also have your private link enabled services. So as a customer, you have this many components to actually deal with. So it is of utmost importance that you know how to monitor and troubleshoot your network. So that said, how do you get visibility into all of the traffic that's flowing through these components? We start off with Amazon VPC Flow Logs. Flow Logs is a feature that enables you to capture information about the IP traffic that's flowing through the network interfaces in your VPCs. You can create a flow log for an Elastic Network interface attached to a resource that is an EC2 instance or a gateway, or you can create flow logs for all ENIs within a subnet or a VPC. And thereafter, you can publish it either to CloudWatch logs or S3. Then you can analyze, visualize, or derive actionable insights about your traffic thereafter using downstream native AWS services. Or you could use one of the several AWS partner solutions like Seam Solutions, or you could build your own downstream pipeline to process your flow logs, or you can use open source solutions like Kibana. Let's take a quick look at what some of these downstream solutions actually are. For logs delivered to CloudWatch logs, you can use CloudWatch Log Insights or Contributor Insights to visualize time series of your flow log data. For flow logs delivered to S3, you can either use Amazon Athena or you can visualize it using QuickSight, both of which is something that I'll be demonstrating shortly. Or you can process your flow logs through something like an Elasticsearch and then visualize it through Kibana. Apart from this, we also have a set of AWS partners that have deeply integrated solutions such as Splunk, Sumo Logic, StealthWatch, and so on. And I highly encourage you to take a look at these solutions which are available on our AWS Marketplace. Now, let's take a look at what a flow log actually looks like. Your flow logs are comprised of flow log records, which are essentially log events, right, consisting of metadata fields that describe a traffic flow or a 5-tuple within a certain aggregation interval. For example, these are a set of flow log records comprising of the default metadata fields. So you see information about the 5-tuple, the number of packets and bytes that have been transferred between the start and the end timestamp, which defines the aggregation interval. You also know whether the flow was accepted or rejected, and then the account ID and interface IDs as well. Apart from these default fields, we've also recently launched a set of enriched metadata fields that give you quick and actionable insights without having to join with other data sources. For instance, we have resource IDs, that is VPC ID, subnet ID, or instance ID to get aggregated views. TCP flags, that's very helpful to infer directionality of your TCP connections, the connection originator. The type of traffic, the packet level IP addresses, which are useful to identify the packet source and destination address, which is the intended source or destination when your flow is going through a middle box, like say a NAT gateway, or even for your EKS workloads where you want to identify the pod level IP. And then we have location metadata that gives you aggregated views based on, say, the region, availability zone, or your local zone, wavelength zone, or outpost ID. Recently, we've also launched the ability to aggregate your flow logs at smaller intervals of 1 minute rather than the default intervals of 10 minutes, thereby giving you granular visibility for troubleshooting, as well as you end up receiving your flow logs a lot faster, which is helpful for quicker detection and remediation of security threats. Now let's take a look at for what use cases you can actually use these flow logs, right? Firstly, one of the most popular use cases among our customers is to use flow logs to gain operational visibility into your network dependencies or traffic patterns. You can use flow logs to troubleshoot network connectivity issues or your data transfer charges. You can use flow logs to rapidly detect security threats and respond to anomalies in your traffic flows. Or you can choose to archive your flow logs for compliance or record keeping purposes and ad hoc analysis. Now let's dive into an example of how you can actually use your flow logs with the packet level IP address field for a security use case. Let's consider a simple environment such as this, where you have an EC2 instance that is talking to the internet through a NAT gateway, and you have flow logs enabled with all of the enriched metadata fields. Now, if you look at the flow log, even though the 5-tuple indicates that the destination address is actually the NAT gateway's address, if you enable packet destination address, you see that that is the actual internet IP that your EC2 instance is trying to talk to. And if this happens to be a malicious IP, you can now choose to alert yourself and remediate by adjusting your security groups. Now let's dive into an actual demo. I'll show you how you can derive actionable insights from your flow logs using Athena and Amazon QuickSight. So we have a simple setup of a couple of VPCs here that span 2 availability zones. We have a few instances in the private and public subnets that are talking to each other, and they're talking to the internet through the internet gateway and the NAT gateway. In our public subnet, we have our which is where we want to analyze our traffic patterns. So we collect flow logs for both of these VPCs and we publish it to our Amazon S3 bucket. And then I'll show you how you can query these logs through Amazon Athena and then visualize these logs through Amazon QuickSight. Let's take a look at this on our console, right? These are our 2 VPCs. We've enabled 1-minute flow logs. We're publishing it to S3. We've enabled all enriched metadata fields like TCP flags, availability zones, and so on. Now we create a corresponding table for the subscription in Amazon Athena. And then now we import that table as a data set into our Amazon QuickSight environment. Now let's look at some cool visualizations on our QuickSight. So this is our first visual. So this essentially tells you the top talkers or the top 10 IP addresses that the web server is sending the most amount of egress traffic to. And it also tells you the volume of bytes being sent to each. And this you can derive with the default metadata fields. However, if suppose you're only interested in east-west traffic flows, you don't want to get a view based on IP addresses, but you actually want to understand the dependency between instances or instance IDs in your VPC network, you can use the enriched metadata field instance ID to get aggregated views like this. So this is a graph that shows you the amount of traffic that's flowing from your web server to each of these instance IDs. Another common use case from flow logs is to aggregate bytes by this enriched metadata field, which is availability zone ID, to troubleshoot your data transfer charges. So this graph shows you how much egress traffic from our web server, which lies in availability zone 4, is actually intra-AZ, which is not charged, how much is inter-AZ, which is charged, and how much is going out to the internet, which is also charged. Now, if you don't want flow level information and rather would like to have connection level information, where you want to try and understand how many connections were initiated externally that got accepted or rejected by your web server, you can use the enriched metadata field TCP flags. And it's particularly useful if you want to understand the directionality of your traffic or if you want to troubleshoot overly restrictive or permissive security groups. Lastly, you don't actually need QuickSight visualizations. You can always use just Amazon Athena to run queries and derive the same set of insights. So for instance, this is a query that gives you the top talkers from your web server. By the way, here's a real example of how you can use flow logs. One of our customers, Netflix, has actually written this blog about how they use flow logs in an extremely scalable manner. I would highly recommend taking a look at this. They explain how they use flow logs delivered to S3 in conjunction with their application metadata to build a complete application dependency matrix. So flow logs was about monitoring your flows and traffic patterns, right? However, there are some times when monitoring your flows is not really enough. You might need either deep packet inspection capabilities, or you might want to take a look deep into the payload, right? How can you actually achieve that? Well, we have a solution for just that. That's VPC traffic mirroring. You can think of traffic mirroring as essentially a fiber tap in the cloud, right? It enables you to get deep visibility into your VPC traffic for use cases like deep packet inspection or threat detection. Let's take a quick look at how traffic mirroring actually works. So suppose you have this EC2 instance with both inbound and outbound traffic, and this happens to be a critical workload in your VPC that you need to monitor. So first, you will need to create a monitoring instance with a monitoring appliance installed. Thereafter, you can create a traffic mirroring session that essentially starts copying traffic that's flowing through the ENI on your traffic mirroring source and sends it out to this out-of-band security or monitoring appliance. Now, this monitoring appliance can either be installed with one of the AMIs available on AWS Marketplace that one of our many AWS partners have developed, or it could be your own packet analyzer, or you could use open source solutions like Zeek or Suricata. In fact, I'll be doing a demo of how you can use Suricata with traffic mirroring shortly. Let's take a look at what are the several AWS partner solutions that we have. These are all our partners, ExtraHop, Vectra, Colite, and so on, that have deeply integrated solutions with VPC traffic mirroring. Let's now take a look at how you can actually configure traffic mirroring. So there are essentially three main components in traffic mirroring: the traffic mirroring target, the filter, and the session. Now let's take a look at each of these in detail. Your traffic mirroring target is essentially the destination of your mirror traffic, and it can either be an elastic network interface that is attached to another instance, or it could be a network load balancer. A thing to note here is that this target can either be in the same VPC as your mirror source, which is where you're receiving production traffic, or it could be in a different VPC or even cross account if you want to deploy in a manner that's centralized for your monitoring solution. Another thing to note is if you're sending traffic from multiple sources to the same target, I would highly recommend using a network load balancer and putting an auto-scaling group behind it, because that way you don't have to worry about scaling it, and it automatically scales up and down based on the volume of traffic that has to be mirrored. Now let's go to the second component, which is filters. Filters are essentially like NACL rules that define which subset of your traffic should be mirrored. right? In this example, we're mirroring only the inbound packets and not the outbound traffic. Why use filters at all? Why can't we just mirror all the traffic always, right? Well, mirror traffic actually accounts for your instance bandwidth allowance. So if the allowance is exceeded, then your production traffic does get prioritized and your mirror traffic can start getting dropped. You can actually track this using CloudWatch metrics as well. However, if you want to ensure that you're always mirroring a certain subset of your traffic, then using filters would be your best bet, because then you know that you're not overloading your instance in times of congestion, and you have a higher probability of actually receiving these packets on your monitoring appliance. The last component is the traffic mirroring session itself. Session is an entity that binds the traffic mirroring source, which is where you receive the production traffic, the filter, and the target, which is the security or monitoring appliance. Now let's take a look at what are the key benefits of this feature, right? Why do customers prefer traffic mirroring? Firstly, rather than having to install and manage third-party packet forwarding agents, with traffic mirroring being a native solution, you can significantly simplify your operations and scale easily using this feature. Secondly, given this is a native feature, there are other benefits too. Right? It significantly improves your security posture, because these mirrored packets are being copied right off the ENI, which means there's no way to tamper with it from the user space like you could in case of an agent-based solution. And lastly, you now also have a wide range of options to choose from for your monitoring appliance. So you're not locked into a particular agent-based vendor, and you can have different applications for different types of traffic monitoring. Now, we've taken a look at two monitoring solutions so far. So let's just do a quick recap of the differences between the two. Flow logs is essentially aggregated metadata about each flow or 5-tuple, and it can be sent to CloudWatch logs or S3. But traffic mirroring is a copy of the actual network packet, right, with the payload. And traffic mirroring sends this copied packets to either an ENI attached to an instance or to a network load balancer. Now let me show you a quick demo of how you can use both these solutions in conjunction, flow logs as well as traffic mirroring. So this is our demo setup. We have 3 web servers hosting a simple web app that takes in a username and password login information. We have VPC flow logs enabled for that entire subnet where our web servers exist. We have now configured a CloudWatch alarm to be triggered each time there is traffic from a malicious IP. And we have written a serverless application module that gets triggered by this CloudWatch event. And what it does is it reactively creates a monitoring instance with a Suricata-based AMI installed. It also has Elasticsearch and Kibana installed on it. And it reactively also enables traffic mirroring on all the web servers within the subnet where we've enabled VPC flow logs. The monitoring instance has Suricata, Elasticsearch, and Kibana, as I mentioned. So when traffic mirroring is configured, you can then go ahead and visualize insights about your traffic or the kind of attack that you're under using Kibana. The serverless application module that we've written is actually on our GitHub repository. I've provided the link here. I do encourage you to try it out yourself. You can also customize this to terminate your monitoring instance and terminate your VPC mirroring sessions if and when you realize that the CloudWatch alarm is no longer being triggered. Now let's take a look at this on our console. These are our 3 web servers, and we've created 1-minute flow logs. This time we're publishing it to CloudWatch logs. And on CloudWatch logs, we've used contributor insights to configure a rule that triggers a CloudWatch alarm each time there's traffic coming from a set of custom threat list, right? Custom malicious IP. Now let's go to that malicious IP and trigger a couple of simple SQL injection attacks, a couple of apostrophe attacks, a couple of double quote attacks. And now if we were to take a look at our CloudWatch console, you see that the alarm has now been triggered, right? Which also means the serverless application module has been triggered. And therefore, if you take a look at the traffic mirroring console, we now see 3 sessions created for each web server. The filter is we're mirroring all the traffic and we're sending it to a central target that is installed with Suricata, Elasticsearch, and Kibana. Now let's take a look at our Kibana dashboard. So on the Kibana dashboard, you can see that in the last 10 minutes, we've received a total of 22 attacks. We can see a split of how many of these attacks were made on each web server. We can also see a split of what type of attack was made, right? Apostrophe attack versus SQL injection attack. And you can also visualize your Suricata logs on the Kibana dashboard, which means you have access to the actual payload. And if we were to copy that payload, and if we do a simple base64 decode, then you will be able to see the actual HTTP request that was made that was trying to extract your login information. So that was an overview of how you can use two of our monitoring solutions to get visibility into your network traffic flows. Now next, how do you track the network performance of your EC2 instances? How do you know if your network bandwidth has been exceeded or if you're seeing packet loss? For that, EC2 provides a couple of tools. First of all, EC2 provides CloudWatch metrics that enable you to monitor network bytes in or out and packets in or out of all the network interfaces on an EC2 instance. In addition, a new feature is that EC2 now also provides network interface level metrics that track when traffic exceeds its fair share of allowance on an instance. So here's an example of the command that you can run on your Linux instances and query these metrics on demand, right? And these metrics are essentially real-time snapshots of the number of packets that were discarded since the last time your ENA driver was reset, because either the bandwidth in and out allowance was exceeded or PPS was exceeded or contract and so on. You can also install a CloudWatch agent on the EC2 instance and create custom metrics in CloudWatch to track these metrics. What are the use cases of these metrics? You can use them to monitor your network performance of EC2 instances. You can use it to benchmark the network throughput so that you can choose the right instance sizes for your workloads. Or you can use it to troubleshoot network issues and diagnose the root cause of any sort of packet loss. So we've learned how you can monitor both your network traffic flows as well as your network performance. Right, with these tool sets, you decide to now go ahead and grow your footprint on your AWS network, and you start deploying increasingly complex architectures. However, when you do this, you might have run into situations where it can become quite tricky to ensure that your network configuration actually matches your intent. And not all of us are network or security admins, so misconfigurations can often occur, and when it does occur, it can result in network connectivity issues between your VPC resources. And these connectivity issues can have significantly high resolution times because it's even difficult to identify that it's being triggered by a misconfiguration. So how do you ensure that your network is always properly configured and actually secure? To achieve just this, we are very excited to launch a brand new VPC feature, VPC Reachability Analyzer. Reachability Analyzer is essentially a configuration analysis tool. It allows you to determine reachability between any two resources in your VPC. If the path between those two resources is unreachable, then Reachability Analyzer also provides explanations to identify the details of the blocking component. So you can use that to troubleshoot an unreachable path. Apart from troubleshooting, you can also use Reachability Analyzer for configuration intent verification or automated validation. Now let's see all of these use cases in action. Firstly, troubleshooting. Let's say we've created a brand new VPC, we've added an internet gateway, we've opened the security group and NACL, and we're trying to SSH into the instance. It all looks fine, but when we try to SSH into it, we realize that we're unable to connect to our instance. So to troubleshoot this, we can now use Reachability Analyzer and specify the internet gateway as a source and the instance as a destination to determine and debug why exactly we are unable to SSH. So let's take a look at this on our console. Here's Reachability Analyzer on our console, and we create and analyze a new path. We're trying to debug SSH connectivity, so we name it accordingly. And as mentioned, the source here is an internet gateway, and the destination is the EC2 instance that you're trying to SSH into. And because it's SSH, we specify port 22. Now, Reachability Analyzer tells us that the path is indeed not reachable. So why is that? Along with the reachability status down in this Analysis Explorer, you will also find what component is actually blocking the instance and the internet gateway path. So here it says that there is this particular route table that doesn't have an applicable route to the internet gateway. So what you can do is you can go and add a new route in this particular route table and then troubleshoot again, and now you should have reachability. Now let's look at the next use case, which is intent verification. A common design pattern is to have your VPC separated into 3 tiers and have each of these tiers in their own subnets: web, app, and database tiers. In such an architecture, you might want to have some implicit security properties that should always hold true. For example, you might want to make sure that no instance in your database tier can directly talk to any instance in the web tier. However, while you might intend to configure this, how can you be sure that your intent is not violated? For that, you can use Reachability Analyzer and input the source as an instance in your database tier and the destination as an instance in your web tier. Let's take a look at it on our console. So we click on Create and Analyze Path. This time we're trying to debug connectivity between the database and the web. And both the instances in this, both the source and destination in this case are EC2 instances. We don't specify a port because we don't want any path to exist at all. And now we see that accidentally there is in fact a path between the web and the database. So the security property that you intended is actually not holding true. So what do? You can now look at the Analysis Explorer and see all the components that are actually allowing the path between these two endpoints. And now you can determine which security group, or NACL in this case a security group, is actually allowing this path. And we can go into this security group and we see that there is a rule that's allowing outbound traffic. We can tighten that and try this path again so that it becomes unreachable. Another use case, automated validation. Reachability Analyzer allows you to define multiple path analysis that can be reused on an ongoing basis. So for example, you can explicitly define reachable properties that you think should always hold. For instance, your web and database tier should never be able to communicate. Your dev and test environment should always be able to communicate, right? And you can express these as analysis that you can then integrate as part of your deployment or Canary infrastructure. And using this, you can ensure that your intent is never violated as and when there are configuration changes made in your organization. Let's briefly understand how Reachability Analyzer actually works. Unlike traditional reachability analysis tools, Reachability Analyzer does not actually send packets between the two endpoints. It uses automated reasoning to actually build a model of the network configuration and determine reachability properties of your network. And in these examples, we've shown simple components, but apart from them, Reachability Analyzer can also reason about components such as your load balancers or peering connections or transit gateways. So that brings us to the end of this session. Quick recap, we've learned how you can monitor your network traffic flows using VPC flow logs, how you can gain deeper visibility into the payload using VPC traffic mirroring, how you can monitor the network performance of your EC2 instances using EC2 instance level metrics, and finally, how you can troubleshoot your network connectivity issues using the all-new VPC Reachability Analyzer. So that's basically it. Thank you so much for watching, and I really hope you're able to go and give all of these solutions a try yourself. And I highly encourage you to also please submit your feedback through the session survey. Thank you.